So, as you observed from the examples, the context insensitive analysis is sometimes quite imprecise because of the ignorance of context information. Okay. Then the question is, how can you achieve a more precise analysis? Let's design context sensitive analysis that distinguishes different calling contexts. Okay. There are actually many ways in practice to achieve context-sensitive analysis. But in this lecture, let's use the most common and intuitive approach based on call string. Okay. A call string is an ordered sequence of call site. So we will use this ordered sequence of call site as a representation of a context. What does that mean? Okay, then let's see the same example here. But now, instead of merging all the continuations and instances into a single element, we will differentiate all of them. Okay. So after the function call at line 11 here, we will have this continuation and the abstract memory. Okay. Here I omit the instance and environment here because they are rather trivial. Okay. So as you can see, this memory has an entry of variable x, which is associated with its call site 11. Okay, that is the call string that represents the current context. Okay, that means this x is especially the instance after the function call at line 11. Okay. And the next step will be similar as before. It propagates the memory to the next label. For the next function call to the sum function, okay, in this time the parameter is associated with a new call string that is prepended by 6. Okay, so the call string for the new context is 6,11. That will be used to denote the instance of x in this particular calling context. Okay, this one. And its behavior is similar to the concrete execution. It again propagates the memory to the next label. Again, the new instance of x is created with the new calling context, which is 6,6,11 here. Okay. And then we also, okay, we will differentiate each instance of global variable at a certain program point. Okay, which means that so at this particular context, the value of z at line number 4 will be 0. Okay, makes sense. And then once it reaches the return statement, okay, the next target is computed based on the continuation. So here, what is the topmost continuation? That is label 6. Okay, so it propagates the abstract memory to the next label of label 6, which is 7. Okay, so the abstract memory at label 7 is updated accordingly. So as you can see, the abstract value of global variable in the callee is correctly propagated to the caller. Okay, and it will maintain a separated instance of global variable for this particular context. Okay, and then it returns to label 7 according to the continuation. Okay. And then again, the abstract value of global variable in the callee is propagated to the caller. So from now on, we also maintain a separate instance of global variable for this particular context. Okay, and then the value of z at line number 8, okay, for this particular instance is computed precisely. And then finally it returns this memory to the label 12, which is the correct return site of this particular function call, right? Then after this propagation, you can see the memory at label 12. Okay, As you can see, the abstract value for C after the function call is the most precise estimation of that of the concrete semantics. Okay. So far we have seen how the context insensitive and context sensitive analysis behave. Okay, let's compare pros and cons of two approaches. Context sensitive analysis is much more precise than context insensitive analysis, but it is in general more costly because it requires more computation, right? We need to compute a lot of information compared to this one. Okay. And more seriously, the context-sensitive analysis may not terminate if an infinitely long call string is involved in, as you can see. So the most common approach is to use partial context sensitivity. That keeps only the top most k continuations. Okay, this approach is so-called KCFA, where k is the length of continuation to keep. Okay, if k is equal to 0, then it is the context insensitive analysis, and if k is equal to infinite, then it is fully context sensitive analysis. Okay, so if we pick a reasonable and finite k, then yeah, we can instantiate partially context sensitive analysis. Here is the definition of the abstract instance domain, that is the power set of call strings whose lengths are shorter than k. Okay, so here is the definition of the abstract continuation domain, again that preserve the topmost k continuations. Okay, then let's see the abstraction and concretization functions. The abstraction of a set of continuations is a set of length k prefix. Okay, then this set is always a finite set because a program always has a finite number of call sites, right? And their finite combination also finitely many. Okay, the concretization function makes a potentially infinite set of concrete continuation, and the prefix of all of them is the abstract continuation. Okay. Then let's define the abstract semantic operators for function calls. First, memory binding. It will make new instances of the parameter with the given abstract instance. Okay. And next, new environment will be also created based on the given instance, abstract instance. Okay. Next, the important thing is the push context. It will push a new element to the continuation, okay, but it will only keep the latest k element and cut out the remainings. Okay, that is our design of partially context sensitive analysis with topmost k context, right? It will maintain only length k context. The other important thing is that the abstract instance. Again, here we also use k-limit call string as abstract instance. Okay, so both of the case we will only keep the latest k. Okay, here the k is a hyperparameter. The semantics of semantic operators for returns, okay, which is the pop context function here, which is defined as follow. There are two cases, right? Usually for each element in the abstract context, there are actually two cases. First, if this abstract continuation contains an element, okay, then we can use the element to compute the next target and restore the old environment. Okay, but what if the context is empty? Then it may be empty because we always limit it may be empty because we always limit the length of context to k. right? So sometimes if the execution has deep nested function calls, say k plus 1 nested function calls, and then returns from the topmost k function, then where should we return after the initial function call? Okay. In that case, the analysis has the same behavior with the context insensitive analysis. Okay. Which means that it conservatively considers all possible call sites for the current function. Okay. So in short, this k-limit context sensitive analysis has the same behavior with the fully context sensitive analysis if the call depth is less than or equal to k. Okay, but it cannot restore the old history beyond the latest k context. Okay, in that case, each behavior is the same as the context insensitive analysis. Okay, then let's see how the partially context sensitive analysis work when k is equal to 1. Okay, here is the same example as before. So as I mentioned, if k is equal to 1, then the analysis keeps only the last k, which means last one calling context, right? So let's consider these abstract transitions. Okay, first in function f, the analysis, okay, completely separate the instances of x based on the call string, right? Which means that this x is an instance from the call at line 1, okay, and the other x, this one, is an instance from the call at line 2, okay. But see the abstract memory in function g here, okay, because it forgets the context beyond length k, right? So the abstract memories are merged together. Okay. Here, as you can see, two memories through call context 1, 2, 3. Okay, one memory is from this calling context 1 to 3. Okay, the other one should be 2, 3 here. Okay, these two memories will be merged together. Okay, so two abstract values for y, okay, will be merged into this one. Okay, interval 1, 2, 3. In the same way, so two abstract value for y when the last call site is 4, okay, this one, they are also merged together. So it will result in interval 2 to 4. Okay. So because of this abstraction, right, the return values are also collapsed. So all the instances of variable v and w, they have interval 1 to 4, right? And finally, the abstract values for a and b are interval 2 to 8, which is still very imprecise. Okay. Then, what if this k is larger than 1? Okay. Consider the same example and the same abstract transitions. But now, the analysis also differentiate instances in function g, okay, as well as those in function f. So you can see we differentiate everything, right? Because of this, the analysis can compute precise return values like this, okay, and then finally it can compute the most precise abstraction of the concrete semantics, okay, for the variables in main, and finally we reach the fixed point. Okay, let me summarize this lecture. So in this lecture we have learned how to handle advanced programming features like pointers and functions. Okay? They are actually crucial part for precision and scalability in practice. There are multiple possibilities for abstraction of such advanced features. In this lecture, we have covered most common schemes like allocation site-based heap abstraction and call string-based context abstraction.